Hey everyone, welcome back to the channel. Today we're diving deep, and I mean really deep, into the fabric of reality itself. We're talking about quantum foam, a mind-bending concept that could rewrite everything we know about the universe. Imagine a universe where empty space isn't actually empty. Instead, it's a turbulent sea of energy, bubbling and churning at the smallest scales imaginable. That's the essence of quantum foam, a realm where the laws of physics as we know them might completely break down. Hold on tight because we're about to explore a world where virtual particles pop in and out of existence, mini black holes flicker for the briefest of moments, and the very structure of space-time becomes a chaotic dance of energy. This is the universe at its most fundamental, and it's going to blow your mind. So, what exactly is quantum foam? It's a concept that was first proposed by physicist John Wheeler back in the 1950s, and it's rooted in the strange world of quantum mechanics. You see, in the quantum realm, things aren't so clear-cut. Empty space, the vacuum of the universe, isn't really empty. Instead, it's filled with what we call quantum fluctuations. Imagine a pot of water that's just about to boil. You see tiny bubbles popping up and disappearing on the surface. That's kind of what's happening in quantum foam, but instead of water, it's the fabric of space-time itself that's bubbling. These bubbles, my friends, are filled with energy, and according to Einstein's famous equation, EMC2, energy, can be converted into matter. So these quantum fluctuations are constantly creating tiny particles, virtual particles we call them, that pop in and out of existence in the blink of an eye. Now we're talking about scales so small, so unbelievably tiny, that they're almost impossible to comprehend. We're talking about the Planck scale, which is about 10 to the minus 35th meters. To give you some perspective, that's like comparing the size of an atom to the entire observable universe. At this scale, space-time itself becomes fuzzy, uncertain. It's not the smooth, continuous fabric we once thought it was. It's more like a foamy, turbulent sea, constantly in motion. And it's this foam, this quantum foam, that could hold the key to understanding the very nature of reality itself. Alright, so we've established that quantum foam is weird, really weird. But how does it actually work? Well, buckle up because we're about to dive deeper into the quantum rabbit hole. Remember those virtual particles we talked about? They're not just some theoretical concept, they're a direct consequence of one of the most fundamental principles in quantum mechanics, Heisenberg's uncertainty principle. This principle states that there's a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time. The more we know about one, the less we know about the other. Now, in the vacuum of space, this uncertainty means that the energy of the vacuum can fluctuate wildly over very short periods of time. These energy fluctuations are what give rise to virtual particles, pairs of particles, and antiparticles that pop into existence, only to annihilate each other an instant later. Think of it like this. Imagine you have a perfectly balanced seesaw. Now imagine that the seesaw is constantly being nudged up and down, creating tiny imbalances in the balance. These nudges are like the quantum fluctuations, and the brief moments where the seesaw tips one way or the other are like the virtual particles. But here's where things get really interesting. These virtual particles aren't just passive bystanders. They can actually interact with real particles, influencing their behavior in subtle but measurable ways. For example, the Casimir effect, a well-established phenomenon in quantum physics, is thought to be caused by the pressure exerted by virtual particles on two closely spaced plates. It's like the virtual particles are pushing the plates together from the outside. So, even though we can't see quantum foam directly, we can see its effects on the world around us. It's a constant reminder that the universe is far stranger and more mysterious than we could have ever imagined. Okay, so quantum foam exists, and it's even weirder than we thought, but does it actually matter? Does this microscopic, bubbling froth of space-time have any real impact on the universe as we know it? Well, that's the million-dollar question, and physicists are working tirelessly to find out. And the answer, my friends, could revolutionize our understanding of the cosmos. You see, one of the biggest mysteries in physics is how to reconcile quantum mechanics, the theory of the very small with general relativity, Einstein's theory of gravity, which governs the very large. These two pillars of modern physics seem to be fundamentally incompatible. General relativity describes gravity as a smooth, continuous curvature of space-time, while quantum mechanics tells us that the universe is fundamentally granular and uncertain at the smallest scales. So how do we reconcile these two seemingly contradictory views? This is where quantum foam comes in. Some physicists believe that the fluctuating foamy nature of spacetime at the Planck scale could be the key to unifying gravity and quantum mechanics. Imagine trying to build a smooth ramp out of Legos. You can get pretty close, but at a certain scale the inherent blockiness of the Legos becomes apparent. In the same way, quantum foam could provide the fundamental Lego blocks from which smooth continuous spacetime emerges at larger scales. This could have profound implications for our understanding of black holes, those enigmatic objects where gravity is so strong that not even light can escape. At the singularity of a black hole, where matter is compressed to an infinitely small point, the laws of general relativity break down. But if quantum foam is real, it could provide a way to understand what happens at the singularity. Instead of a point of infinite density, the singularity could be a fuzzy, turbulent region of spacetime governed by the laws of quantum gravity. Quantum foam is a tantalizing concept. If we could prove its existence, it would revolutionize our understanding of the universe. But how do you even begin to detect something so incredibly small, so deeply woven into the fabric of reality itself? Well, it's not easy, but scientists are a clever bunch. They've devised some ingenious experiments to try and catch quantum foam in action. One promising avenue is to look for its effects on light traveling from distant objects. Imagine spacetime as a perfectly smooth surface. Light would travel across it in a straight line, undisturbed. But if spacetime is foamy, if it's constantly bubbling and fluctuating, then light would be jostled and jiggled as it travels. This jiggling, while incredibly tiny, would cause a slight delay in the arrival time of light from distant objects like quasars, the incredibly bright cores of active galaxies billions of light-years away. Now, we're not talking about delays that you could measure with your wristwatch. These delays would be on the order of femtoseconds or quadrillionths of a second. But with incredibly precise instruments like the Hubble Space Telescope, astronomers are actively searching for these tiny temporal distortions. Another approach is to crank up the energy. Particle accelerators like the Large Hadron Collider smash subatomic particles together at incredible speeds, recreating the extreme conditions that existed just moments after the Big Bang. At these energies, physicists hope to see subtle deviations from the predictions of the standard model of particle physics, deviations that could be a telltale sign of quantum foam. And then there are black holes. These cosmic monsters are natural laboratories for testing our understanding of gravity at its most extreme. Some physicists believe that studying the behavior of black holes, particularly the way they evaporate over time through Hawking radiation, could provide clues about the nature of quantum foam. So, while we haven't directly detected quantum foam yet, the race is on. With each passing year, our instruments become more sensitive, our experiments more sophisticated. It's only a matter of time before we unlock the secrets of the universe's tiniest secret. The possibility of quantum foam's existence is thrilling. It's like standing at the edge of a new frontier, peering into a realm where the known laws of physics might crumble. What wonders await us if we dare to venture further? If quantum foam is real, it would rewrite our understanding of the universe at the most fundamental level. It would mean that spacetime, the very fabric of reality, is not a smooth, continuous sheet but a turbulent, ever-changing sea of quantum energy. Imagine the implications for our understanding of black holes. These enigmatic objects, once thought to be inescapable prisons of gravity, might actually be portals to other universes connected by wormholes woven into the fabric of quantum foam. And what about the Big Bang itself? Our current models of the early universe break down at the moment of singularity, the point of infinite density and temperature from which everything emerged. But if quantum foam is real, it could provide a way to understand what happened in those first fleeting moments of creation. Perhaps the universe didn't begin in a singularity at all, but emerged from a quantum fluctuation in the pre-existing quantum foam. The implications are staggering. It could mean that our universe is just one of countless universes, constantly bubbling into existence and disappearing within an even grander multiverse. And then there's the question of wormholes. These hypothetical tunnels through spacetime, often relegated to the realm of science fiction, could become a reality if quantum foam exists. Imagine the possibilities: interstellar travel, time travel, the ability to explore the farthest reaches of the cosmos. Of course, these are just possibilities, tantalizing glimpses into a future shaped by the mysteries of quantum foam. But one thing is certain: If we can prove its existence, it would usher in a new era of physics, an era where the seemingly impossible becomes possible. Quantum foam is a fascinating and bizarre concept that suggests space itself is constantly shifting at the smallest levels. While we haven't detected it directly yet, future experiments could reveal whether this bubbling spacetime is real. Could quantum foam hold the secret to the fundamental nature of the universe? Could it be the missing link between gravity and quantum mechanics, the key to unlocking a unified theory of everything? Scientists are on the hunt for answers, and the journey promises to be as mind-bending and awe-inspiring as the universe itself.